I'm going to do an example now with a simple transformer EMF. And the example is a stationary single turn square loop is exposed to a time-varying magnetic field. And the geometry of the situation is such that the loop lies in the XY plane, and there is a uniform Z-directed magnetic field everywhere around here. So this is my loop, and it's square, and the length of its sides are A, like that. Now the first thing that I'm asked to do, oh, and there's, the loop has a little gap in it with a resistor. It's not perfectly conducting all the way around, so that we can find the current in the loop. So the first thing I am asked to do is, in fact, find the current in the loop. How do we do that? We got to remember, first of all, we can use that based on Ohm's law. So if we have this resistance R here, the current is going to be the induced EMF divided by that current, divided by that resistance, sorry. Which means now all we have to do is find V EMF by applying Faraday's law. And we know that that is minus the time derivative of the flux integral of that magnetic field. So, the magnetic field that we have is equal to some amplitude constant B0 times sine of omega t, where omega is our radian frequency and t is time, as usual. And it's z-directed. Now, nothing about our loop is changing, which means that nothing about this surface integral is changing, right? There's not going to be any change to the bounds of this flux integral, and there's not going to be any change to our vector ds. The only part that is going to change is b. So we can rewrite this integral as minus the surface integral over that surface excuse me, that should be a partial. Of the time derivative of the magnetic field dot ds. And then we can start substituting in the values for these things. So that is equal to minus integral from 0 to a. I didn't say where in the xy plane we exist, but there's no reason for it not to be 0 to a, since everything is constant everywhere. That time derivative evaluates to omega b0 cosine of omega t z hat. And then we dot that with our surface normal vector, which for a loop in the xy plane, depending on the direction we choose for the loop, can be either positive z or negative z. I'm going to choose positive z, which means that's x, that's y. Do your right-hand rule, you find that the z-axis is pointing out of the board, so the z direction is that way. Again, applying the right-hand rule, if our surface normal vector is out of the board, that means the direction of the contour here is counterclockwise, as we're looking down on it like we are. Evaluating this integral, let's see, we've got the dot product, which evaluates to 1. We have a bunch of things that don't depend on x or y, so that can move out to the front. And then we have an integral from 0 to a of dx and an integral from 0 to a of dy. So what we get as a result is minus a squared omega b naught cosine of omega t. And that is equal to the induced EMF. But we're not looking for the EMF. We're looking for the current. So we're going to have to divide that by the resistance of our loop. Luckily, our loop is a perfect electric conductor with a resistor built into it, and the resistor's value is R. So that current is equal to V EMF over R, or minus a squared omega b naught cosine of omega t over R. Now for part 2, we're asked to assume that the loop is placed such that the angle between the surface normal vector and that time derivative is some angle that's not 90 degrees. It's an arbitrary angle, theta. What that means is if we're looking at a side view of the situation, here's the z-axis, here's the x-axis. If we draw our magnetic field in orange here, that means that from a side point of view, our loop is lying no longer in the xy plane anymore. It's at some kind of angle, and ds looks like that, and it makes an angle with the magnetic field, and that angle is theta. If the loop is in an angle with respect to the magnetic field, what that means is that inside our Faraday's law integral, this dot product, which if you remember, since the only thing that's time varying in this equation is b right now, that's going to be the same as writing it this way. So the dot product with the time derivative of the magnetic field and ds is, they're not going to be in the same direction. So the result of that dot product is going to be partial b, partial t, magnitude of that times the magnitude of ds times cosine of the angle between them, because that's a fact that we remember about dot products. In that case, the resulting current works out to be all the same stuff as before, minus a squared omega b naught cosine omega t times that cosine of that angle, all divided by the resistance in the loop. The rest of this problem are a couple of conceptual topics that we need to talk about. First of all, in part 2 here, we cared about the vector direction of that time derivative, not of the magnetic field itself. And the reason for that is, yes, it is possible for these two things to be in different directions. In a simple case, you could have a phase difference here so that maybe there's a sign change, or maybe they're just out of phase. But in a more complicated difference, you might have two different vector components of B with different time dependence. So even though these two vector components have the same amplitude, when you take the derivative of the y component is going to be 10 times the derivative of the x component in amplitude. The last part of this example is what are the phase and direction of the current relative to that time derivative of the magnetic field? Now, if you remember our initial drawing, we had the magnetic field being z-directed, which means that's pointing out of the board. I'm not going to draw it everywhere because I need to draw this loop. And the time derivative of the magnetic field is also z-directed, but it's got a different amplitude and phase. Now, recall that we defined our surface normal vector pointing in the positive z direction. So it's pointing out of the plane, and that means that this contour goes in this direction. VEMF, going back up, well, I'll just restate. According to Faraday's law, VEMF, which is equal to this closed contour integral of E dot dl, note the lack of a minus sign here, is equal to minus the time derivative of that surface integral, that flux integral of B dot ds. That flux integral of B dot ds. And that's S, and that's on the contour of S, the boundary of S. So, if this time derivative of the flux is z-directed, and it has a minus sign, that means that VEMF has to be in the minus right-hand rule direction of the time derivative of the flux. So VEMF causes currents in a direction to oppose the change in EMF. Oh, sorry, the change in flux. And this is an important statement whose name is Lenz's law. For the sake of our particular problem, that means that let me draw the voltage on, let me draw the voltage on our example diagram here. That would be that way, which would mean, since it's a source, we would have a current going that way along the direction of the contour. And remember that that current is minus a squared omega b naught cosine omega t over r. So our current is opposing the direction of the change in magnetic flux. And we're using the right-hand rule to check that.